There's this hidden energy all around us, not in things themselves, but just in how they're arranged. Today, we're going to dive into exactly that, the world of electrostatic potential energy. We're going to build a system of charges right from scratch to see how it works. All right, so here's how we're going to break this down. First, we'll get a handle on what potential energy actually is. Then, we'll build a super simple two-charge system, see what happens when we add more, and then, this is the fun part, we'll tackle a really neat example with a square of charges. And of course, we'll wrap it all up with the key formulas you'll want to remember. So, what is electrostatic potential energy really? Well, imagine you get to play architect of the universe for a day. The potential energy is just the total amount of work you have to do to build a setup of charges, grabbing each one from way out at infinity and putting it in its final spot. Let's start with the absolute simplest case we can think of. Picture a completely empty universe. Nothing, nada, zip. Our job is to place just two little electric charges into this void. We'll call them Q1 and Q2. Okay, so first up is charge Q1. We bring it in from infinity and, well, that's it. Since there's nothing else around, there's no electric field to push or pull against, it's a freebie. The work needed is zero. Costs us absolutely nothing. But now things get interesting. When we go to bring in our second charge, Q2, the game has changed. That first charge, Q1, is now creating its own electric field. So to bring Q2 closer, we actually have to push against that field. We have to do work, and that work gets stored as energy. You see, that first charge creates something we call an electric potential. The best way to think about it is like an invisible electrical landscape. Our first charge has created hills and valleys all around it, and every single point in space now has a specific potential value, V. And here is the absolute key takeaway. The work we did pushing Q2 into place doesn't just disappear into thin air. Nope, it gets bottled up, stored right there in the system as potential energy. And calculating it is easy. It's just the charge you're moving, Q2, times the potential it's moving through, V1. And that leads us right to this beautiful formula. The potential energy, U, is that constant 1 over 4 pi epsilon naught, don't worry, that's just a number to make the units work out, times the product of the two charges, divided by how far apart they are. Now think about it. If the charges are the same, like two positives, you had to push them together, so the energy is positive. But if they're opposite, they attract, the field does the work for you, and the energy is negative. Makes sense, right? Okay, two charges, that's pretty straightforward. But what happens when we want to add a third charge into the mix? Well, the great news is the logic we just learned scales up perfectly, all thanks to a really cool idea called the superposition principle. When we bring in that third charge, Q3, it doesn't just feel the effect of Q1 or Q2. It feels the combined effect of both. It's like it's navigating two electrical landscapes at the same time. And the total potential it feels is just the sum of the individual ones. Super simple and super powerful. That's superposition. So to find the total energy of the whole system, you just have to be a good bookkeeper. You calculate the energy for the first pair we made, Q1 and Q2. Then you calculate the energy between Q1 and Q3, and finally the energy between Q2 and Q3. Just add up the energy for every unique pair, and that's your total. All right, that's enough theory for now. Let's get our hands dirty and see how this actually works with a concrete example. We're going to build a square of charges. So here's our mission. We need to figure out the total work it takes to put 4 charges on the corners of a square with sides of length d. And notice they're not all the same. We have a positive q, then a negative q, then another positive q, and a final negative q at the corners A, B, C, and D. Let's build it piece by piece. Putting that first charge at corner A, freebie, costs us nothing. Now we bring the negative q to corner B. It feels the pull from A, so there's some work involved there. Then comes the positive Q to C. Now it has to deal with the potential from both A and B. And you can see where this is going. That last charge at D has to contend with all 3 others. So how on earth do we arrive at this final answer? Well, it's back to our bookkeeping. We have to find and sum up the energy for every single unique pair. Let's count them. You've got 4 pairs along the sides and 2 pairs across the diagonals. That's 6 pairs in total. You just have to carefully calculate the energy for each one, remembering the side lengths are d and the diagonals are d times the square root of 2. Add them all up, do a little algebra, and voila, you get this expression. Okay, but now for a really cool follow-up question. What if we wanted to place a 5th charge? Let's call it Q0, right in the dead center of that square. How much work would that take? And the answer, amazingly, is zero. None. How is that possible? It's all about symmetry. At that exact center point, the positive potential created by the two positive charges is perfectly canceled out by the negative potential from the two negative charges. The net potential is zero. The electrical landscape is totally flat right there, so it's a free ride.
Ooh, all right. We've definitely covered a lot of ground. So let's just take a moment to step back and summarize the key formulas we've been working with.
It really all comes down to a simple pattern. For two charges, you have one energy calculation to make. For three charges, you have three unique pairs, so you sum up three terms. And for our square with four charges, we had to find all six possible pairs. The rule is always the same. Find every single duo, calculate their potential energy, and add it all up. And that leaves us with one final thought to chew on. We've spent all this time talking about the work you put in to assemble this system, to store all this energy. So here's the question. If you were to just let go and let all those charges fly apart, how could you get that energy back out? Something to ponder. Thanks for watching.